Good morning, everyone. I'm delighted to welcome you all today. My name is Dr. S.K. Singh, and I hold a PhD in this field. Today, I will be talking about the calibration of the HPTLC MS system. This is a crucial process that ensures our analytical methods are accurate and reliable. Over the course of this presentation, we'll explore the key steps involved in calibration, discuss best practices, and look at some practical examples. I look forward to sharing this knowledge with you and engaging in some insightful discussions. Let's get started. Welcome to this section where we focus on calibration. Calibration is a crucial step in our analytical process because it helps ensure that our results are both accurate and reliable. When we calibrate our instruments properly, we can trust that the data we obtain truly reflects the sample we're analyzing. This is especially important for quantitative analysis, where precise measurements are essential. It also plays a key role in maintaining overall system performance, preventing errors before they happen. Now, calibration isn't just a one-time thing. It applies across different modules and interfaces. For example, the HPTLC module needs calibration to deliver precise chromatographic results. Similarly, the MS module relies on calibration for accurate mass detection. And of course, the interface itself must be calibrated to ensure seamless communication between components. In essence, calibration acts as a foundation for quality in our analytical workflows. It's vital for producing trustworthy results and keeping our systems running smoothly throughout their operation. Let's take a closer look at our calibration strategy. Since we're dealing with a multi-component system, it's essential to calibrate each module individually to ensure that every part is accurate on its own. But that's not enough. We also need to perform an integrated system calibration to make sure all components work together seamlessly. This process includes two main aspects: instrument calibration, which involves ensuring that our measuring devices are providing accurate readings, and analytical or quantitative calibration, which helps us relate the responses we measure directly to known reference standards. It's important to remember that calibration isn't a one-time task. We perform these calibrations at defined intervals to maintain reliability over time. Now, let's talk about the core concept of calibration itself. Essentially, calibration is about establishing a clear relationship between the measured response from our system and the true value, which we determine using a reference standard. This process is vital because it helps us achieve three key goals: accuracy, which ensures our measurements are correct; precision, meaning our results are consistent; and linearity, so our system's response changes proportionally with the true value. All of this ties back to our overall goal: to produce reliable, trustworthy measurements that support sound decision-making in our work. Let's talk about densitometer calibration. First, we need to focus on calibrating key aspects like wavelength accuracy and photometric linearity. Ensuring these are precise is crucial because they directly impact the reliability of our measurements. To verify these calibrations, we typically use standard filters or certified materials, which act as trusted benchmarks. This way, we can be confident that our densitometer provides consistent and accurate readings, supporting reliable quantification in our analyses. Now, moving on to HPTLC-MS calibration. It's equally important to calibrate the HPTLC module itself. We look at parameters such as the sample applicator volume accuracy, which ensures we're applying consistent sample amounts every time. We also check the plate migration distance, so our migration is reproducible across runs. And of course, the scanner wavelength accuracy, which is vital for precise detection. To achieve this, we use reference dyes and standards, which serve as our calibration tools. These standards help us confirm that the RF values are reproducible, ensuring our results are consistent and comparable over time. Overall, thorough calibration at each step is what guarantees the reliability and precision of our analytical methods. Let's talk about ion source calibration. This step is crucial to ensure that our ion generation remains stable throughout our analysis. When we say stable ion generation, We mean that the ion source consistently produces ions at a steady rate, which directly impacts our data quality. Two key parameters here are spray stability, especially in electrospray ionization, and the voltage settings. Maintaining consistent spray stability and correct voltage adjustments helps us achieve reliable sensitivity and reproducibility in our results. If these parameters fluctuate, our measurements can become inconsistent, which we definitely want to avoid. Moving on to MS module calibration, this is all about fine-tuning the instrument's critical parameters. Mass accuracy, which is how precisely we measure the MZ ratio, is fundamental. Resolution, or the ability to distinguish between close MZ values, is also vital. And, of course, sensitivity, or how well the instrument detects low concentrations, plays a big role in our overall performance. Calibration is typically performed using standard calibration mixtures. These are specially prepared solutions with known components, which help us verify that our instrument is reading correctly. Usually, we do this calibration daily or just before starting an analysis session to ensure everything is in perfect order. Finally, it's important to remember that calibration isn't just a one-time task. For our HPTLC MS system, regular calibration helps maintain accuracy and reproducibility across all our analyses. By consistently checking and adjusting these parameters, we ensure our data remains reliable and our results trustworthy. Let's talk about interface calibration. This step is crucial because it ensures an efficient transfer from HPTLC to MS. When we calibrate the interface properly, we improve the consistency and reliability of our results. One of the key aspects we check is extraction efficiency, meaning how well our sample is transferred and prepared for analysis. If this step isn't optimized, we risk losing important compounds or getting skewed data. We also focus on reproducibility, which is about making sure the process yields consistent results every time we run it. Consistency is essential for trustworthy data and meaningful comparisons. By properly calibrating the interface, we can prevent sample loss, which might happen if the transfer isn't smooth, and contamination, which could compromise the integrity of our samples. Overall, this calibration step ties directly into our goal of obtaining accurate, reliable, and reproducible results, supporting the integrity of the entire analytical process. Now, let's take a look at the analytical calibration curve. This curve is constructed using standard solutions at different concentrations, which helps us establish a relationship between the response we measure and the actual concentration. When we plot response versus concentration, it provides a visual representation of how the instrument reacts to varying amounts of the analyte. One of the key requirements here is linearity, which is outlined in ICH-Q2 guidelines. This means we want a straight-line relationship, indicating consistent response across the range of concentrations. To quantify this, we look at the correlation coefficient, R2, which should typically be greater than or equal to 0.99. This high value confirms that our calibration curve is very linear and reliable for quantification. Overall, this calibration curve is fundamental because it ensures our analytical method is accurate and precise over the concentration range we're interested in, supporting the validity of our entire analysis. System suitability testing is a critical step that we perform before starting any analysis. It's essentially a check to ensure that our system is operating correctly and reliably. The key parameters we look at include the peak area precision, which tells us how consistent our measurements are for the same sample. Then, we assess RF consistency to confirm that our compounds are eluting at the same retention factors each time. Mass accuracy is also vital, ensuring our instrument is measuring the correct masses precisely. Additionally, we evaluate the signal-to-noise ratio to confirm that our signals are strong enough to distinguish from background noise. Altogether, these parameters help us verify that the system is ready to produce valid, reproducible results for our analysis, maintaining the integrity of the entire process. Let's talk about documentation and compliance. First, it's essential to keep accurate records, such as calibration certificates and calibration logs. These documents prove that equipment is functioning properly and meets quality standards. Additionally, standard operating procedures, or SOPs, are vital to ensure consistency and clarity in our processes. Now, compliance isn't just a matter of good practice. It's a regulatory requirement. We need to adhere to 21 CFR Part 11, which governs electronic records and signatures, ensuring data integrity and security. Plus, we follow the ALCOA Plus principles, which emphasize that our data must be attributable, legible, contemporaneous, original, and accurate, with additional factors like complete, consistent, enduring, and available. All these elements come together to support our overall goal of maintaining high quality, integrity, and regulatory compliance in our operations. Let's talk about calibration frequency and maintenance. First, the frequency of calibration is crucial to ensure our instruments are always accurate. For daily tasks like MS tuning, it's important to calibrate every day to maintain optimal performance. Then, for periodic checks, especially of HPTLC components, we perform calibration less frequently, but still regularly. After calibration, there are additional maintenance steps to consider. This includes maintenance after relocating the instrument, which helps prevent any issues caused by movement or handling. Also, this is the time to perform preventive maintenance, things like cleaning, inspecting, and replacing worn parts, to keep everything running smoothly. Overall, sticking to these calibration and maintenance schedules is key to ensuring the reliability and accuracy of our analytical results, supporting the integrity of our work throughout the entire process. So, in conclusion, I want to emphasize that calibration plays a crucial role in ensuring the accuracy and reliability of our results. When we calibrate properly, we can trust that the data we generate is solid and consistent. It's also essential for maintaining regulatory compliance, which is vital in our industry. Now, especially with HPTLC, MS systems, calibration becomes even more important because it requires the integrated calibration of all modules involved. This integration ensures that every part of the system works harmoniously, providing us with precise and valid analytical results. This overall process is not just about technical accuracy, it's fundamental for quality control. It helps us deliver trustworthy results that meet regulatory standards and support sound decision-making. So, in summary, proper calibration is the backbone of reliable, compliant, and high-quality analytical work. For further support, please feel free to contact us. We're here to help clarify any questions or provide additional resources you might need. Thank you so much for your time and attention today. I truly appreciate your engagement and interest. Remember, we're always available to assist you as you apply what you've learned. Again, thank you, and I look forward to connecting with you soon.